And now let's talk about mixed numbers. Mixed numbers are numbers that are made up of an integer and a proper fraction. So you can't have an improper fraction inside of a mixed number. The whole point of a mixed number is to not use an improper fraction. So a mixed number is a combination of an integer and a proper fraction. For example, this nail, let's see, it's 2 whole inches long, but it doesn't go all the way to the 3rd inch. So let's figure out what fraction this is. This longest bar represents the 1/2 mark. So these second longest marks represent the 1/4 marks. So this is 1/4, then this is 2/4 or 1/2, and this is 3/4. So this nail is 2 3/4 inches long. Now note that a negative in front of a mixed number means that that negative has to affect the entire number. So here we have -4 2/3, and we often think of a mixed number as a sum of the integer and the fraction, and that's true. But the mistake students make here is that they sometimes think that if this is negative, that the integer is negative, but the fraction is still positive, and that's not the case. So if you have a negative mixed number, then what you've got is the negative of the sum here. So basically it's unwritten, but there are parentheses here if you write it in a sum form. So it's -4 2/3. And if you distribute that negative, you'd have -4 minus 2/3. It's not the same as -4 plus 2/3, because you see then you'd be subtracting 4 but adding the 2/3. But if you have -4 2/3, you're subtracting the whole thing, subtracting the integer and the fraction part. Okay, for example 7, we're going to practice changing each of the following mixed numbers to the form a over b. So in other words, to fraction form. We're going to convert these mixed numbers to improper fractions, where a and b, of course, would be integers. Okay, so let's do this the long way around. I know that you probably already know the shortcut for converting a mixed number to an improper fraction, but remember what we said earlier. You can't just teach your students the rules to memorize and expect everything to be okay. The rules have to be built on understanding. So what we're going to do is write this out the long way, and you could even use concrete models for this as well, but we're just going to write this out the long way. 4 1/3 is equal to 4 plus 1/3, so we'll need to add these two. And if we're adding an integer and a fraction, of course we're going to need this integer to become a fraction. So let's think of it as 4 over 1 plus 1/3. And we know we need a common denominator. So of course we can use 3. So what would it take to multiply by this 1 to get the 3 that we want? Well, of course we'd need to multiply by 3 over 3. Okay, now this becomes 12 over 3 plus 1/3. And 12 over 3 plus 1 over 3 gives us 13 over 3. So 4 1/3 is equivalent to 13/3. And of course, the shortcut way, the way that you end up doing it in real life, is to do denominator times whole number, that would be 12, and then add the top number to that and leave the bottom number the same. So 3 times 4 is 12, and 12 plus 1 is 13. But when you're trying to explain to students why it works that way, they need this process, and it's even good if you let them model it with a concrete area model or something like that first before they do this. And then after they can do this, then you can go ahead to the shortcut method. Let's work with a negative mixed number now. So we have -3 2/5. So we'll think of this as -3 plus 2/5 in parentheses. So remember, the negative applies to the whole thing. The parentheses are important because that is what makes sure that we understand that the negative is applying to the whole thing, but we'll just work inside the parentheses. Okay, here we have an integer plus a fraction. So we'll need this integer to become a fraction. And now if the denominators are 1 and 5, what's a number that 1 and 5 can both go into? Of course, they can both go into 5. So we'll need this denominator to become 5. So we'll multiply this by 5 over 5. And that's going to give us, inside the parentheses, 15 over 5 plus 2 over 5. 3 times 5 is 15, 1 times 5 is 5. Okay, so now 15/5 plus 2/5 is 17/5, so we have negative 17/5. Now let's check our shortcut. 5 times 3 would be 15, and 15 plus 2 would be 17, and so we would end up here with negative 17/5. And now let's convert the other direction. So this time we're converting 39/5 to a mixed number. So we're starting with an improper fraction and we're going to mixed number form. And all that means is just basically doing the division here. You know that a fraction bar represents division. So this is 39/5, but we can now think of it as 39 divided by 5. So 39/5 becomes 39 divided by 5, and we'll write that in long division form, 39 divided by 5. Okay, 5 goes into 39 7 times, multiply back and subtract, and we have 4 left over. So 39 divided by 5 is equal to 7 and 4/5. See, the 4 is the number that didn't get divided by 5. 5 went into 39 7 whole times, so that's the whole number. And then this 4 is the remainder that has not yet been divided by 5. So we have to express it in fraction form. So 7 and 4/5. Notice you can always check your work here by converting this mixed number back into an improper form. 5 times 7 would be 35, and 35 plus 4 would be 39. So of course that's 39/5, which is what we thought. Now let's talk about properties of addition for rational numbers. Rational numbers have the following properties of addition. First of all, they have closure. Adding two rational numbers produces a rational number. You can never add two rational numbers and get an irrational number. So the rational numbers have closure under addition. Rational number addition is commutative. That is, changing the order of addition does not change the result. In other words, for any two rational numbers, a plus b is equal to b plus a. It doesn't matter what order you add them in. Rational addition has the associative property, which means that the grouping of the add-ins does not change the result. You can group the numbers any way you like and you'll still get the same answer. So if we're adding three different numbers, then we can say a plus b plus c, where we grouped the a and the b together, is equivalent to a plus b plus c, where we grouped the b and the c together. So the grouping doesn't change the result. And then we have the additive identity property. So 0 can be added to any number and the number will not change. Any number plus 0 is still the same number. And we have the additive inverse property, which means that every rational number has an opposite, so that a plus the opposite of a equals 0. So rational numbers have all these properties of addition. Okay, let's find the additive inverses for the following numbers. So in part A we have 3/5. Well, the additive inverse is just a fancy way of saying the opposite. So the additive inverse of 3/5 is going to be negative 3/5. Now notice that the negative, again, goes either in the top or in the front of the fraction. It never goes in the denominator. And notice that I'm not just going to say 3/5 equals negative 3/5, because that would be absolutely wrong. We can't put an equal sign in between two numbers that are not equal. So we're asked to find the additive inverse for 3/5. We need to say the additive inverse equals negative 3/5. Don't use the equal mark as a thing that means now I'm going to do the next step. It doesn't mean next step. It means the same as. So I can't say that 3/5 is equal to negative 3/5, but I can say that additive inverse is equal to negative 3/5. And how do we know that? Because 3/5 plus negative 3/5 is equal to 0. That's what makes these two numbers additive inverses. Now let's look at negative 5/11. So the additive inverse of negative 5/11 is going to be positive 5/11, and that's because negative 5/11 plus positive 5/11 equals 0. And then in part C we have 4 1/2. Of course, that's a mixed number. And you might at first think, well, I have to convert this to an improper fraction to get the additive inverse, but that's not the case. We actually can just get the opposite. So the additive inverse of 4.5 is just negative 4.5. Or if you wanted to convert this to an improper fraction, you could say 2 times 4 is 8, and 8 plus 1 is 9/2. So this number is equal to positive 9/2. So you could say, if you really wanted to, that the additive inverse is negative 9/2. And that would be fine, but it's just not necessary. But both of these are additive inverses of this number, because 4.5 plus negative 4.5 is 0. Or we could also look at it as 9/2 plus negative 9/2 is equal to 0. Either way, these numbers are the additive inverse of 4.5. And now let's talk about subtraction with like denominators. As long as the denominators are the same, addition works the same way as subtraction, as far as we just work with the top numbers and we leave the denominators the same. And let's get a definition of subtraction in terms of addition. If a over b and c over d are any rational numbers, then when we subtract a over b minus c over d, the result is the unique rational number e over f, such that a over b is equal to c over d plus e over f. Now, what does that all mean? Basically, it means that if we subtract two numbers and get this one, then we should be able to take this answer and add back what we subtracted and get back to the original number. And so each subtraction problem only has one answer, is basically the important thing to come away with here. So here's example 10. Find each difference. So we have 5/8 minus 1/4. Now notice that these denominators are different, so we'll need to make these denominators the same. And the least common multiple for 8 and 4, of course, is going to be 8, because 4 does go into 8. So of course 8 is the smallest number that they can both go into. So we'll have 5/8 minus 1/4 times 2 over 2. How did I know to use 2 over 2? Because if the denominator is 4 and I want it to be 8, I have to multiply by 2. And that means I also have to multiply the top by 2. So now we're going to have 5/8 minus 2/8, and of course that is 3/8. 5 minus 2 is 3, and the denominator stays the same. If this number could be simplified, we would do that, but of course it cannot. Now let's look at part B, where we have 5 1/3 minus 2 3/4. Now subtraction with mixed numbers can be a little tricky, and there are some steps for it, but let's just say right now that we don't know the steps, and let's just get around that trickiness by converting both of these numbers to improper fractions. This is not a bad strategy, but sometimes it does cause more work than we would like to do, because the bigger your whole number is, the bigger the top number of your improper fraction is going to be. I'll show you the other method in just a minute, but for right now, let's just say we don't know the rule and we're willing to convert these to improper fractions. So 5 1/3 is going to become 16/3. 3 times 5 is 15, and 15 plus 1 is 16, and so I have 16/3. And then the 2 3/4 will say 4 times 2 is 8, and 8 plus 3 is 11, so this becomes 11/4. Now, we can't do this subtraction yet because these denominators are not the same. So what is the least common multiple for 3 and 4? Well, the smallest number that 3 and 4 can both go into is 12. Okay, so we need to convert both of these fractions to have denominators of 12. So what would I have to multiply by 16/3 in order to get the 12 in the denominator that I want? Of course, I have to multiply by 4. So I'm going to multiply this fraction by 4 over 4. And what would I have to multiply by 4 to get the 12 that we want? Well, we'd have to multiply by 3. So 11/4 times 3 over 3. That's going to give us 16/3 times 4 over 4. Now 16 times 4 is 64. So this is going to be 64/12. And here 11 times 3 is 33. So this is going to be 33/12. And now 64 minus 33 is 31. So that's 31/12. Now, here is a thing about mixed number problems. When you're adding just regular fractions or subtracting regular fractions and you get an improper fraction as your answer, that's okay. But if you're working with mixed numbers and you get an improper answer, you should convert your answer back into mixed number form because it was a mixed number problem. Like the example that I always use with my students is, if you're in America and somebody asks you a question in English, you answer them in English. No big deal. But suppose that you were bilingual. Suppose you could speak English and French, and somebody asked you a question in French, you would answer them in French. If they asked you a question in English, you would answer them in English. Well, we, in a way, are bilingual. We can speak in mixed numbers or we can speak in improper fractions. So if somebody asks us a question in fraction form, it's okay for us to answer in fraction form, even if that fraction is improper. But if somebody asks us a question in the language of mixed numbers, then if we can, we should communicate our answer in the language of mixed numbers. So now I'm going to convert this back to mixed number form. 12 will go into 31 2 times with 7 left over. So 31 twelfths converts to 2 and 7 twelfths. And there's our final answer. So again, just remember that if the question is in mixed number form and you get an improper fraction as your answer, that improper fraction should be converted to mixed number form just to be consistent with the question. Now, still on example 10, here is the alternate method for part B that I promised to show you. This method that I'm going to show you requires more rules. You have to understand the steps, so it's less intuitive, but in a lot of cases it can end up being easier if you do know the steps. And that's because we're going to avoid the large numbers that we usually end up with when we convert to improper fraction form. So when you're working with mixed numbers, it's very helpful a lot of times to write these in a vertical format, and that's because we're going to end up using this idea of borrowing and carrying, and it's easier to see that when you're doing things vertically. Okay, so here we have 5 1/3 minus 2 3/4. Now you can see that the denominators are different, so you know that when we work with adding and subtracting fractions, we have to have common denominators. So let's say we know that the denominator needs to be 12, so we're going to multiply each of these fractions by whatever it takes to get the denominator of 12. So this fraction is going to become 5 4/12. See that? 1 times 4 is 4. Okay, and this fraction is going to become 2 9/12. Okay, now we can do our subtraction and we can say 4 minus 9, 4/12 minus 9/12. Now that should make you pause for a minute because you don't have enough to take away 9. You've only got 4/12 here and you need to take away 9. So basically you don't have enough 12ths. So what you need to do is borrow from the 5. So if I take 1 off of this 5, that will leave me with only 4. And that 1 that we take off, we're going to split into 12/12. And then we also have our 4/12. And then this, of course, stays the same. So you see what we've done here? This 5 became 4 plus 1, and the 4 plus 1 is 4 12/12, but we've also got these 4/12. Okay, now 12 and 4 is 16. So now what we've got is 4 16/12 minus 2 9/12. And you see now that we can do our subtraction. So 16 minus 9 is 7. So we've got 7/12 here. And then 4 minus 2 is 2. So this is 2 7/12. And we got the same answer that we got with the other method, but it's just that sometimes that other method is going to be easier to work with, and sometimes this method will be easier to work with. So both strategies are important. Imagine what would have happened on the other method if our whole numbers had been like 15 and 39 or something. Then changing to improper fraction form would have been a real pain, and we would like to be able to use this method. But if the whole numbers are small, then maybe this method seems like a lot of work, and we can get away from the borrowing and carrying parts of it by just getting into improper fraction form. It's good to be familiar with both ways, and if you end up teaching fractions to maybe 5th or 6th graders, you'll need to teach them both ways of working with mixed numbers. Now here are a couple more examples for us to work with adding and subtracting. Here we've got x over 2 plus x over 3. We know that we have to have a common denominator here, so that common denominator will be 6. and we'll need to convert both of these where the denominators are 6. So x over 2 is going to become x over 2 times 3 over 3, and x over 3 is going to become x over 3 times 2 over 2. That's going to make 3x over 6 plus 2x over 6. Now this time these numerators can be combined. 3x plus 2x is like terms, and we can combine those and get 5x, and then the denominator stays the same. So we end up with 5x over 6. In part B, we have 3 different fractions. 1 3/10 plus 2 3/4 minus 1/5. Now, just to make sure we don't run into any borrowing or carrying, I'm going to go ahead and convert these mixed numbers to improper fractions. So 1 3/10 becomes 13/10, 2 3/4 becomes 11/4, and of course 1/5 is not a mixed number. Okay, now let's go ahead and find a common denominator for all 3 numbers. The common denominator for 10 and 4 and 5. We need a number that all 3 of these can go into. So let's just look through the 10 times table until we find one that will work. 10 times 1 is 10. Well, 5 will go into that, but 4 won't. 10 times 2 is 20. Guess what? 4 goes into 20 and 5 also goes into 20. So our least common multiple is 20. So we will need to convert each of these to a fraction that has a denominator of 20. What do I have to multiply by 10 to get 20? Well, I have to multiply by 2. So 13/10 becomes 13/10 times 2 over 2. 11/4 will need to be 11/4 times 5 over 5. And 1/5 will need to be 1/5 times 4 over 4. And you can see that when we do the multiplications, we'll have the denominators we need. So this is going to be 26 over 20 plus 55 over 20 minus 4 over 20. And now we can just add and subtract. So 26 plus 55 is 81, and then 81 minus 4 is 77, so we have here 77/20. Now remember what we said. This answer is improper, but the question was asked in a mixed number form, so this answer should be converted back to a mixed number form. How many times will 20 go into 77? Well, 20 will go into 77 3 whole times with 17 left over. So this is going to be 3 and 17/20. And there's our final answer. Now let's talk about estimation with rational numbers. Estimation is important because it helps us make practical decisions in our everyday lives. You know, maybe you're in Lowe's and you're trying to decide if it's affordable for you to recarpet your bedroom. And so you've got the price of carpet there, and you don't have the exact square footage with you, but you can kind of estimate how big your room is. You know, that kind of thing is what we use estimation for. Or maybe you're trying to decide which of 2 products is the better buy in the grocery store, and you're trying to do an amount per ounce. Sometimes they have it on the label for you, but sometimes they don't. And are you really going to take a minute and get out your calculator and really do the calculation? Sometimes, but maybe sometimes you might just be able to estimate and see which of the 2 products is cheaper. So estimation is really an important skill, but you'll only be good at it if you practice it. And a lot of the estimation and mental math techniques that you talked about in the whole number sections will also work with rational numbers, so you might go back and review those. But let's also talk about benchmark fractions. Sometimes to obtain an estimate, it's easy to round fractions to a convenient or a benchmark fraction. So we're talking about things like 1/2, 1/3, 1/4, 1/5, 2/3, 3/4, or 1. You know, just the fractions with the easy kind of small denominators. That's what we call benchmark fractions. In other words, if you had a fraction that was like 11/12 or 3/8, you might not work with those larger denominators. You might just kind of round that to something easy to work with. That's what these benchmark fractions are. Let's just estimate a couple of fractions here that have pretty large denominators. So it says estimate the following using benchmark fractions. Well, here we have 59/80ths. And you can just think, well, that fraction won't reduce, but 59 is really close to 60, and if this were 60/80ths, it would reduce. So let's estimate this at 60/80ths, and then you can see that both of these numbers can be divided by 10, which would give you 6/8, and then both of those numbers can be divided by 2, so you would end up with 3/4. So 59/80ths can be estimated as 3/4. And kind of the same thing on 31/90ths. So 31/90ths will not reduce, but if this were 30/90ths, it would reduce, and 31 is very close to 30. So we can estimate 31/90ths as 30/90ths, and then we can reduce that from 30/90ths to 3/9, which reduces to 1/3. So 31/90ths is very close to 1/3. And it would be much easier to do mental math with these rounded fractions than it would be with these fractions that have these huge denominators. You're not going to be able to do much in your head when the numbers are that big and that hard to work with. Okay, here's a little estimation exercise. A 6th grade class is collecting cans to take to the recycling center. Becky's group brought the following amounts in pounds. About how many pounds does her group have altogether? 1 1/12, 3 5/8, 7 3/10, 2 3/5. So we don't want to get an exact answer, we just kind of want to get a ballpark answer. We want to estimate. So one easy thing to do is first we can add all the whole numbers because those are not going to change. 1 plus 3 plus 7 plus 2 gives us a total in whole numbers of 13. So now let's estimate the fractions, and let's start with 3/5. Now notice that 3/5 can't be reduced, but it's really close to 1/2. Half of 5 is 2 1/2, and here we have 3. So this fraction is actually just over 1/2. And let's make that note. Now how about 3/10? Well, 3/10 won't reduce either, but it's something under 1/2. Now, if you look at this fraction, it's very small. This is less than 1/10. If you add this fraction and this one together, you couldn't have any more than 4/10 because this is less than 1/10. So 3/10 plus something that's smaller than 1/10 gives us 4/10. So even if we add these two together, that's still under 1/2. So I'm just going to take both of those together and call them about 1/2. And then here we have 5/8. Now you know 4 is half of 8, so 5/8 is just over half. And so here we have 1/2. These two went together and made 1/2, and then this one over here is about 1/2. So for the fractions, we'll add those 3/2 together and get about 1 1/2. So we already had 13, and now we add our estimated 1 1/2 to that, and we can say that Becky's group collected about 14 1/2 pounds for recycling. And of course, that is approximate, it is not exact. Now let's look at example 13 together, and this is just a little more practice with estimation. It says estimate each of the following additions. Here we have 27/13 plus 10/9. And notice that these numbers are both so unusual for us that this is not something that you would be expected to do mentally, but you can get a really good estimation. And what we want to do is start by thinking about how many times 13 goes into 27. Well, 13 times 2 is 26. So 13 goes into 27 just a little more than twice. So this is a little over 2. And then this is 10/9. So 9 goes into 10 one time with 1 left over. So this is like 1 1/9. Or if we estimate, it's just a little over 1. So if we take 2 plus 1, we can say 2 plus 1 is 3, so the total here would be just a little more than 3. Of course that's not exact, but that's the whole point. With estimation, the idea is to do it quickly and mentally and not get an exact answer. Here in part B we have 3 9/10 plus 2 7/8 plus 11/12. Okay, each of these fractions is very close to 1. 9/10, of course, is just 1/10 shy of 1. 7/8 is just 1/8 shy of 1. And of course 11/12 is just 1/12 shy of 1. So we're going to estimate each of these fractions as 1. And now let's just go through and write out our addition. So here we have 3 plus 1 plus 2 plus 1 plus 1. And that's going to add up to 8. And of course each of these ones is a little overestimated because each of these fractions is slightly under 1. So our total is 8, but we know that it's actually a little large. And so we could say that the total is a little less than 8. And then here's part C. We have 3 7/8 plus 11 1/2 plus 2 2/5 plus 5 1/16. And one thing that is convenient to do a lot of times is to find fractions that add up to something close to 1. So here we have 7/8. And we know that if we had another 8th, those two fractions would add up to 1. 7/8 plus 1/8 would be 1. And we don't have anything exactly an 8th, but we do have 1/16, which is half of an 8th. So 7/8 plus 1/16 is still something a little under 1, but it's very close to 1. And then here we have 2/5, which is just shy of a half, and here we have a half. So this 1/2 and this 2/5 can go together and make something that's a little short of 1. And the wavy equal mark means that we are estimating, we're not getting exact answers. Of course, if I put equals here, just a straight equal mark, I would be saying 7/8 plus 1/16 is the same as 1, and that's not true. So I just put the wavy equal mark to show that we're estimating. Okay, now let's get our whole numbers. So 3 plus 11 plus 2 plus 5. And then let's get our estimated fractions. These two fractions estimated to 1, and these two middle fractions estimated to 1. So we'll add those. And now we add all these numbers together. 3 plus 11 plus 2 plus 5 plus 1 plus 1 is approximately 23. And so that's a look at working with fractions. Remember, fractions are like anything else in life. You need lots of practice and lots of exposure in order to feel very comfortable with them. So when you're teaching, you want to give your students lots of exposure to fractions and let them get a lot of practice with it. And in your own everyday life, I would encourage you to add fractions mentally whenever you can. Think about fractions, think about estimating with fractions, and the more you do it, the easier it will come to you, and the more ways you'll find to explain it to your students and help them to understand it. So good luck, and I will see you in the next video.